Welcome, everybody, to the 30th colloquium, to the 30th anniversary of the ICIPC. Welcome in Colombia. I'm really happy to be able to take part on the colloquium on the digital way. My name is Christian Hopmann. I'm the head of the Institute for Plastics Processing at RWTH Aachen University in Aachen, Germany. We, IKV and ICIPC, we have a long-lasting friendship, which is now 30 years old, or even more longer than 30 years, because already during the foundation of the ICIPC, the contact already existed, and we have been a good friendship. We have a common understanding on how research should be done, on how we focus on industrial application while doing research, and how do we educate? Do we need to educate our students? And thank you very much for this long-lasting cooperation, for this good friendship, and all the best for your future. I'm very sure that the next 30 years and even more will be as successful as the last 30 years and even more successful. I believe that the ICIPC is a really important cornerstone in the national and also in the international research scene of plastic technology, and I'm looking forward to cooperate in the future. So thank you for giving me the opportunity also to contribute to that colloquium by giving a presentation about sustainability in plastic, the global challenges, and the IKV's research. I would like to focus a little bit. So why do we need to take care about sustainability in plastics technology? There's a very simple and a very particular reason: because the population is growing and growing. We are approaching 10 billion people pretty soon. We have been less 1 billion 2,000 years ago, and you see here in that curve that for decades and decades, in millenniums and millenniums, the population has been pretty low. But in just 150 years, the population exploded in Asia, in Africa, in Europe, in North and South America, and everywhere. And that is creating a demand for material. It is creating a demand for fresh water, a demand for food, a demand for clothes to wear, be worn on the body. And of course, everybody needs to have something to live. And that creates a demand in materials, and that creates a demand in plastics, of course. And on top of that, the global middle class is growing and growing. You can see that here on the right-hand side of the chart, how the middle class is growing. The middle class is the class which has, let's say, some money to be able to afford some comfort in life. The necessity of life, water, eating, clothes, and so on, is already covered. And now they are able to spend a little bit more money to make the life more comfortable. So those people are looking for air conditioners, they are looking for cars, they are looking for mobility, they are looking for greater flats and apartments and houses. So again, that is creating a demand for material and a demand for plastic material. And that you can see here in this chart, how the global plastic production increased. I'm sure you know those numbers. If you look just on the polymerescence, it is like 380 million tons. If you add the fibers, then it comes on the level of 450 and even more tons. It doesn't matter how you count it. The trend is clear and the trend is unbroken, and the trend will continue. So we will continue to grow the production and the usage of plastics. And that is causing some challenges, of course. And one particular challenge is not just the pure amount of material, but it's also the lifetime of material. And you can see in the right-hand side of the chart that in many applications, the lifetime is pretty short. In packaging, in consumer goods, in textiles, which account for 250 million tons of material. So more or less half of the material is associated with those applications, and the average lifetime is below 0.5 up to 5 years. In textiles, maybe even shorter than 5 years. On the other hand, you can see that in construction sectors, there's also 65 million tons of material associated with, but here we have a lifetime of 36 years. Pipings in the ground, 100 years, windows 50 years. So long-lasting application which do not cause so many issues like the short lifetime application, like packaging. In particular, packaging, 150 million tons each year are going into packaging application. The trend is growing and growing. together with a growing population on our Earth, of course, in particular for packaging and more specific in food packaging, we use more and more material, but the lifetime is really short. So basically, this material is coming more or less immediately back in to the market as scrap and as a waste. And that we have to take care. Let's have a look on the global plastics flow here in 2018, which is just 5 years ago. So it should more or less represent the figures of today. Total plastics production, just resin at that time, 360 million tons. Then we add some 30 million tons of recycled material, which is a total use of plastics for built as of 390 million tons. Out of that, we produce 385 million tons of plastics good. Then there are some goods still in use. So we generate a plastic waste amount of 250 million tons. That's the amount which can be used for something. The good thing is we collect 175 million tons. So more than 50, much more than 50% of the totally generated waste is already collected, but there's still a lot of amount of 1/3, 75 million tons, which is just unknown. So it is improper disposed to the environment, to the ocean, to the seas, to the rivers, to the environment, and there is some leakage. And that, of course, we have to make sure that we collect this material in the future to be able to at least manage it in an appropriate way. The material which we already collect, we use for landfill, managed landfill, which is the second best option. Of course, landfill is not really an option. By the way, in Germany, the landfill of untreated waste is absolutely forbidden. So we are not allowed to dispose the material to the environment, also not in a managed way. I think we should really take care of this material in the future to use it also as a source for new raw material. I will come back to the point later on. Then we have 50 million tons for energy recovery and 50 million tons for recycling input. Output is then, as I already mentioned, just 30 million tons. That is also something we have to take care and consider. So that means basically, if we look on the ways to use plastics, we have 4 options. We have the first one is, of course, reutilization. So make a new product out of the old material. It might be the same product, it might be the same product for another application. In very, very few cases, you can use the product for a different application. Usually, plastics is not made for that. Plastic application is not made for it because to use the product in a different way, to do a retreatment, the product usually needs to have a specific value. And since the value of plastics products, plastics materials is not so high, we can hardly, let's say, use a huge amount of material for that kind of reutilization. On the bottom, we have what we call the energy recovery. So we use the energy to make the energy stored in an application to make heat out of that, to make electricity out of it, ideally including the use of the carbon, so carbon capture utilization, carbon capture storage, taking the carbon coming out, the CO2 coming out of the energy recovery, which is basically burning the material, collecting this carbon dioxide, storing that into our ground, or making, for instance, polymers out of that. That's a nice opportunity. It costs some money. It's politically not everywhere accepted, but it is a reasonable option to make the plastic compatible with our environment. And then, of course, we have the field of recycling. 2 options as well here: mechanical recycling, doing some regranulation, having new pellets out of the old material, and making new product out of that. Pure mechanics, low energy input, which is of course nice in terms of emissions, in terms of efforts to be put on that, but you cannot do that with every kind of material, because there might be some contamination in the material, there might be some mixed waste, there might also be some composites, fibers, long fibers, short fibers, and so on, then it's really difficult to do mechanical recycling, in particular if it is mixed waste. In this case, we have the option of doing raw material or chemical recycling by gasification, pyrolysis, depolymerization, whatever it might be. We basically cut down the molecules down to the monomers and we do re-synthesization of this material, and basically we get a material out of that which has the same properties like a virgin material. And that is the big difference between chemical recycling and mechanical recycling. In mechanical recycling, we keep the material as it is, making a new product out of that. So we have we have to take low efforts to do so, but the properties of material are very different from the virgin material. In raw material recycling, we have to take high efforts in terms of energy and also in product production complexity, but we get as virgin material out of that. That's the two options. Today, mechanical recycling is by far the most established way for real recycling. Raw material recycling, it's on the way to be developed. There have been some prototype plans on that, but to my best knowledge, the amount of material which is recycled in a chemical way is still pretty low. However, we need to do recycling much more than we do today, because that is our option to make plastic circular. We also have to look on the feedstock side, of course, not just on the mechanics or the recycling side, but also on the feedstock side. And here we can see in this chart today, basically we use 85% plastics coming from a fossil base. So gas and oil is the main base for our plastics. We have a small share, 5%, of where we use the recycling. Then we have a very small share of CO2-based polymers and a share of 10% roughly coming from bio-based sources. By the way, I appreciate very much that within your colloquium you also look into those bio-based materials. I think that's a really a growing market in the future. And that is also reflected here in that chart. You see that our target is, our approach is to get rid of the fossil-based material. So fossil-based material is not an option in the long run. We want to have a decarbonization, defossilization of the polymers to get circularity in the material. We need to significantly increase the recycling. There's so much material already in our ground. We have to dig it out and make new polymers out of that in a mechanical recycling process, in a chemical recycling process, but always we will have some losses, and those losses we need to compensate by using bio-based materials and by using CO2-based materials. It's from today on 27 years to go, which is not a long time, but there is a chance to get a real circular, fossil-free, decarbonized or defossilized plastics material into plastics economy. And that is our big chance. So let's talk about recycling, because bio-based you cover, CO2-based is a story for the chemistry, but for the engineers, of course, recycling. That's the opportunity, and for the plastics engineer, more specific, the mechanical recycling. That's the big chance, and we have to take care of that one. Here we have some very important, let's say, key action areas for a sustainable use of plastics. We need to design the product for a minimum product environmental footprint. So the footprint a product is putting on our environment needs to be low. And therefore we need a reduction, as I already mentioned, of fossil-based raw material usage, or a reduction of raw material usage in general. We need to increase them in recycled material input, biomass, CO2, as I already mentioned that. Because today we start from, let's say, very pure, very nice and very well specified raw material, and we can make a film out of that. The highest quality input material, the highest material quality input is going into the films. After using the material for a film, we make maybe some containers out of it. We make some boxes and we make some bins. And you see also the color of the application, they change. And at the end, we burn the material. So basically, we are doing a kind of downcycling. Of course, we have the opportunity from the bin at the end by using chemical recycling to do upcycling and to reuse or recreate new polymers where we can produce a film on. But the most important thing is to keep the material as long as possible on the top of this spiral here. Sooner or later, the material is degrading. The polymer chains are getting shorter and shorter. Impurities are coming in and so on. So the material will experience the spiral, but the longer we can keep the material on the top of the spiral, the more friendly it is to our environment. That means we need to design the product in a more resilient way. We need to design the processes in a more resilient way that they are capable to adapt to the material properties of recycled material. And of course, for recycled materials, we have no specification. For new material, for virgin raw material coming from fossil sources in particular, but also biomass material, you get a nice specification from your supplier on what is the properties of your product. But for recycled materials, you buy some recycled materials, you don't know what is inside. You hardly get a specification. And we made, and still are going on to investigate that. So we are actually buying material from the market, from different suppliers, from different lots, from different seasons of the year, recycled material. Always it's called PELD, and then we investigate what is inside, and that is really interesting. You buy a material PELD recyclate, you produce a film out of that, and then you do your investigation. What you find is there is a major share of PELD inside, but there's an even bigger share of PELLD inside. And there is a share of PEHD inside. So the full collection of polyethylene you will find inside, which is not really nice, but not too hard to process because the melting points are similar, viscosity not too far away. That works pretty well. But then we also find some polypropylene. And for polypropylene, we know that the melting point is much higher, the viscosity is different, the chemical compatibility between polyethylene and polypropylene is difficult, and so on. So polypropylene within polyethylene, that's an issue for film production, in particular for blown film production, depending on the amount of polypropylene, of course. Then we see printing inks, we see lamination adhesives, we see barrier materials, EVA, EVOH, polyamide, PET, we see aluminum, we see wood, we see fillers, we see inorganic, all those different materials, and they are creating a mixture of material, and depending on the combination of the material, we find a lot of impact on the film, the visual impact, mechanical impact, thermal limitation, and of course also a distinct odor, which is not really nice. So let's dig a little bit deeper when we look into our film and try to understand what is inside our film. We find a large number of impurities, as I already mentioned. We find gels, highly oxidized, in general coming from the polyethylene, which is hard to remove by standard processing routines. So we find a share of about 30% of high molecular or even cross-linked polyethylene. We find 1 to 15% of polypropylene. We find 2% of ash content coming from calcium carbonate, from talcum, from titanium dioxide, and so on. So the conclusion is, first of all, we need to have a much better sorting to sort out the different polymers, to differentiate between polypropylene and polyethylene, in particular between polyethylene LD, HD, and LDPE, and so on. We need better washing, we need better recycling processes, we need much more knowledge about all the impact the material experiences during the recycling and also during the usage of the material, let's say during the entire life cycle. And we need to find the right product for the use of this recycled material. And one important thing is we need to have a production process which is capable to handle all the different materials. Of course, we can sort out the pure polyethylene, the pure PELD, and make film out of that. The question is what happens with the rest? There will always be rest. So we need to do something with the rest. And herefore, we need processes that are capable to handle material properties which are not very well defined and not very well specified. And here we need to have what we call resilient processes. And we develop what we call a cross-phase control methodology for the injection molding process. In the injection molding, we have usually two phases. The first is the injection phase. The second one is the holding pressure phase. Everybody who is familiar with injection molding knows it pretty well. In injection phase, the screw is controlled by the screw speed controlled, and in the holding pressure phase is pressure controlled. And then in between, we have a switch over point. And everybody who does injection molding knows that finding the right position for the switch over point is difficult. And it depends very much on the property of the polymer, on the viscosity, on the PVT behavior, and so on. So every time we change the material, we need to change the process. And specifically, we need to adjust the switch over point when we use the same material but different lot sizes having different properties, in particular different viscosities. And that is getting even more difficult when we use PCR, so post-consumer recycled material, because the viscosity is totally different from one lot to the other, and also within one lot, the viscosity may fluctuate frequently. So with our new approach, by having a cross-phase control methodology where we do not have a switch over point, we can also eliminate all the inconsistencies which come along with the switch over point. And we can very nicely do batch-to-batch fluctuation as also fluctuation within one batch. And for that, we get a much more robust production when producing or processing PCR. Here you can see the result. We did some investigations with different settings of the machines, cavity temperature, melt temperature, holding pressure, and dosing volume for two different materials, for two different PCR grades. We call it batch 1 and batch 2. And then we have the conventional control system of a fully electric, pretty modern injection molding machine, and secondly, the same machine but using our approach of this cross-phase control system. And in comparison, you can easily see with the circles the weight of the parts for the conventional control strategy are varying pretty intensely. Whereas for the cross-phase control methodology, we have for the same material very, very stable weight of the part. So that means a very reproducible process and superior quality for the cross-phase control system compared to the conventional one. That means that the cross-phase approach is much better capable in handling the different viscosities, the different PCR grades than the conventional one. In conclusion, in injection molding and other processes, we need to make the processes more resilient against fluctuating properties, and the cross-phase control system is one approach to succeed in that regard. Okay, now we have our process. We know how to handle the material. The question is now, how do we know what grade is a supplier is delivering? We do not know that, because nobody knows what happens along the entire value chain. The raw material producer is creating a raw material with a specific molecular weight, specific viscosity, specific color. The compounder is adding some additives, might it be migrating or not migrating additives, some stabilizers, some anti-block, some whatever colors, for instance. Then the processor, the converter, is creating a, let's say, a co-extruded film. Therefore, he is using a specific recipe, so adding different polymers and different additives, creating different film thickness and different layer distribution. Also, maybe he is already adding some recycled content to the film. Then it goes to lamination, where we have glue, we have printing, we have in the filling maybe some fatty goods coming into the package. It goes to sales, where we have effects of storage time and storage condition. And then there comes the user, the customer, who is finally using the material, the package, yeah, in the intended use, but maybe also in a non-intended use. Yeah? So in a bottle, in a water bottle, there's maybe some oil stored for a specific time, what we call then repurpose of the material or the use of the product. But of course, substances can migrate into the product, and the one who is doing the recycling, the collecting, and the sorting now has to differentiate all the different grades, all the different ingredients, and all the different storage and usage cycles. But at the end, nobody knows what happened before. The compounder does not know what the raw material producer really did. The processor doesn't know what the compounding company did, and in particular, he doesn't know what the raw material supplier has been done. So there is no information. We have really a lack of detailed information along the value chain, and that prohibits very much the recycle of material and also the design of a packaging for a more sustainable solution. And that we want to overcome with our research. So together with partners, we develop something what we call the digital product passport. Like in a standard passport, yeah, remember your passport, the government decided which information is stored in the passport. It describes you personally pretty nice, because there's a picture, there's a name, there's a surname, there's a place of birth, there's a your address, and so on and so on. So if you read the passport, you have all the important information of your personality. And the same we are doing here for our plastics product. We want to store all the information which is required to do proper recycling and to, let's say, create a material, recycled material, which is good enough to be used in technical application. And for that, we are using what we call the EPCIS system, the Electronic Product Code Information System. That is the standard, which is on the one hand specifies a data model, and on the other hand interfaces to capture and create so-called the IPCIS events. And an event might be the manufacturing, the commissioning, quality control, sales, or whatever it is. And for each event, information can be added into that passport. So there is a description when the material has been produced, where it has been produced, what has been produced. But now we add some recycling extension. So what material goes into that has been gone into the packaging, for instance, an LLDPE, an HDPE, there's some titanium dioxide, we can store NFR, and we can describe whether or not there has been some recycled or bio-based content. Whatever you want to add, you can add. And the nice thing is that the IPCIS system is not really new. It's well established, worldwide available. It's developed by the GS1 Association, which is a non-profit network. So that is not a new system, but new is that we add all the recycling information. And when we now have this digital passport, we can have what we call the digital twin, which is basically a digital representation of the entire value chain and all the information each player along the value chain, each manufacturer of a specific step can add the recycling important information, the recycling relevant information into the digital twin. And everybody who has access to this platform, to the information, can then deal with those information. And that helps us to do the assessment of the product's environmental footprint, which is important and getting more important because the customers will ask for that, definitely. And secondly, we can assess the impact of recycled material content on the processing, on the product properties, and so on. So we have a perfect digital representation of the product and of the processes. And by that, we can then increase the recycling content in our product because we know what is going on for safety reason, for quality reason. That is so important. And by having the right quality of the recycling material, by having processes which can handle the recycling material, by doing the right product design, and by providing digitally all the information which are required to support the first three items, we can then increase the the amount of circular material and the amount of circular plastics. So let me come to some final remarks. First of all, I hope I could show you that we really need to have a massive use of recycled carbon, which is really important for a fully circular economy. We need to reduce the fossil-based carbon and replace it by recycled carbon, by bio-based carbon, and to a certain extent as well by a CO2-based carbon. We see that the number of influences. Sustainable production, flexible recycling needs to have a holistic approach. We need to cover the entire value chain, the entire material flow, and for that we need to understand what's in the material. We need to have data on that, and we need to collect the data, and we need to provide the data. And for that we need to have what we call an IOP, Internet of Production, where we do specific research on. We see a large number of impurities in our recycled material that may cause local defects. For that reason, we need to have, on the one hand, a better understanding of what is inside data, and on the other hand, we need to have processes that are capable to adapt to the fluctuating material properties. The white spot, the blind spot, is still the consumer, so us, and also we need to have some, let's say, education on the consumer, and we need to also to have some information on what is the consumer usually doing with the material to better understand what is going on and to take that into account by reprocessing the material. At the end, final remark, we need to have a massive increase of low carbon energy supply to eliminate the CO2 emissions, because plastic processing is an energy intensive production, and as long as we use coal and oil and gas and so on, and we emit CO2 into the atmosphere, the circular economy is not really closed. So we need to have a circular economy on the material plastics, and we do have sustainability in energy supply. And if we do succeed in both cases, the plastics technology is really accepted by the environment and hopefully then also in the longer run by the society. So with that, I would like to thank you all for your attention and your patience. I would like the German Research Foundation for the sponsorship of the research we are doing. And once again, thank you very much to Dr. Flores and all the nice colleagues from the ICIPC. Have a big party tonight. I think it's really a big success you have to celebrate. And hopefully we will see pretty soon in Medellin or in Aachen or wherever it might be. All the best to you. See you. Bye-bye.